Well, thank you very much, Joaquin. Thank you all to be here. Uh, well, first, well, we are all friends here, so I have this English talk in writing paper, so perhaps I have to read something, but it's very nice to talk with all you. I must say, it's really nice. I'm very happy with all friends here. So, what what's my intention of this talk? Well, I will try to explain you some question that we had with Professor Arturo and Nahia, and also with Tomás and Roman, and also with Nahuel Albarracin. And well, I will try to give some answer of the question that we have. So that's more the idea. So I divide the talk in three parts. So the first part, I will try to convince you why you have to study Banach Lipschitz operator ideals. The second part, I will talk about Banach Lipschitz operator ideal, and I will tell you that there's a natural way to construct a Banach Lipschitz operator ideal from a linear operator ideal that is using the RNLS space. So we will give a brief discussion about this space. And also then we will see there's a relation between Banach Lipschitz operator ideal and Banach linear operator ideals. And then finally, I will try to convince you why we don't have to study Banach Lipschitz operator ideals. So that's the plan of this talk. So I will start with the same slide that used Alejandro Chavez 3-4 months ago, talking about nonlinear theory of Banach spaces. The fundamental question of this theory of nonlinear Banach spaces is how much of the linear structure of a Banach space is determined by its metric extractor. The first result in this direction is from Mazur and Ulam from 1932, and state that even if a real normal space and you have a surjective map from E to F that is an isometry and maps 0 to 0, then the function is linear. And as a consequence, E and F are linear isomorphic. This means that the linear structure of a Banach space is completely determined by isometries. So if we want to deal with this question of the fundamental question of the nonlinear theory of Banach spaces, we have two issues to solve. First is how we can describe a linear property of Banach space that we want to see if it's determined or not by the metric structure. And the second is how we can describe the metric structure of a Banach space to see if it affects the linear structure or not. There are many ways to answer these questions. Some of them they can be found in the survey of Carlton and the survey of Godefroy, Lancien, and Sisler, and in the book of Benjamini and Lindestrauss. I think that these two surveys and the book are very well written, and they have a lot of information in this direction. So anyone who wants to start studying this type of problems, you always have to read these three articles of surveys and books. So how we will describe linear properties? Well, we will use the theory of Banach operator ideals. And when I say Banach operator ideal, we say Banach linear operator ideals, of course, in the sense of pitch. I put here three examples of how we can use the linear operator ideals to describe properties. The first says that if a Banach space E is reflexive, if and only if all linear operators from E to E are weakly compact. The second states that a Banach space E has the approximation property if and only if all compact operators from any Banach space F to E are approximable. And the third is Grothendieck's theorem that states that all linear operators from little l1 to little l2 are absolutely summing. Why I choose these three? Well, the first example states that to say a linear property of E, of a fixed Banach space E, we have to consider all linear operators, but from E to E. The second is, it's again, if you have to say something about the Banach space E, you have to consider not only the operator from E to E, if not the operator from any Banach space to E. And the third says something like there's a sort of linear connection or linear property between little one and little l2. So there's something here, a connection between these both spaces that says that every linear operator must have some property. Of course, to say this property, we have many other ways to describe this property, well, but where we use just linear operators. And also, using linear operators, we can describe almost all linear properties of Banach spaces. I put here some examples: the Schur property, Dunford-Pettis property, Radon-Nikodym property, and many else. So, how we can describe the metric structure of a Banach space? Well, we will use Lipschitz map. And that is because there's an open question in this theory that states that if two separable Banach space E and F are Lipschitz isomorphic, thus both spaces must be linearly isomorphic. Well, here we take a separable space because the non-separable case was answered by Haroni and Lindström in 1978. So what is this open question tell us? Well, this is that at least for separable space, we don't know if Lipschitz map determine all the linear properties or not. So if we can see, we don't know what happened with Lipschitz map in relation with linear properties. So that's why we will use Lipschitz map. So we will introduce some notation. With Lip0, we say all the Lip0 from E to F are all Lipschitz maps from E to F that map 0 to 0. And from now on, we will always, when I think in a Lipschitz map, I will think that F maps 0 to 0. When the range space is R, we denote it by E numeral or E hashtag. I don't know how we say this. It's the Lipschitz dual. And note that all linear operators from E to F is a closed linear subspace of Lip0. Now we have a definition for a fixed Banach linear operator A and a class I of Lipschitz function. We will say that the Lipschitz class A extends A if for all Banach spaces E on if we have that all linear operators that belong to the class I are exactly those which belong to A. Okay? So, what we will do with all this? Well, this is the idea. First, we take two Banach space A and if, and two Banach operator ideal A and B, such that we have this equality. Here, we are fixing the linear property or the linear relation that are between E and F that we want to extend to a metric setting. Then, we take two classes of Lipschitz function, IA and AB, which extend A and B respectively, but not any classes, if not some classes that have such a, for example, a Lipschitz ideal property. For instance, here I choose, for say something, that is closed under composition on the left here, by any Lipschitz function. That is, if we take a function in the class and we compose on the left with any mapping Lip0, the composition is still in the class. So what we are doing here, we are trying to see if we can extend this first property where we fix to a Lipschitz setting. Now here comes the hard part, try to prove this equality. And this is the really hard part, because if we show this equality, then we can take E tilde any Banach space which is Lipschitz isomorphic to E, then using the Lipschitz ideal property, we can obtain this equality. And then since IA and AB extend A and B, we obtain this equality. Note that we obtain that all the operators in A from E tilde to F are exactly those which is in B from A tilde to F, and this is exactly the linear property that we have at the beginning. But this, what's different here, that E tilde is Lipschitz isomorphic to E. So here we are saying that this property, this linear property, can be expressed, can be described using Lipschitz functions. Okay, so for us, what will be a Lipschitz map? What will be a class of Lipschitz mapping that satisfies a Lipschitz ideal property? Well, we will take the Banach Lipschitz operator ideal, which was defined by Achur, Reda, Sanchez Perez, and Yahi, and also defined by Cabrera Padilla, Chavez Dominguez, Jimenez Vargas, and Villegas Vallecillo, both independently in 2016. So the question that we start is, why we study Banach Lipschitz operator ideal is to see that if any linear property that we have for Banach spaces, we can extend it to Lipschitz, we can describe it using Lipschitz ideals, Lipschitz functions, and of course Lipschitz functions are not linear. So we are describing a linear property. We are going to describe linear properties using nonlinear descriptions. So here we have the definition of Lipschitz operator ideals. A subclass I of Lip0 is a Lipschitz operator ideal if we always consider those operators with from A to F. We have that is always a linear subspace of Lip0. The identity of the linear of R is always in the ideal, and here we have the ideal property. If we have a function in the class and we compose on the right with a Lipschitz function and on the left with a linear function, then the composition is still in the class. First note that here we don't need it to be a Banach space. It here can be a metric space, and in fact the original definition of Lipschitz operator ideas is when the domain space is a metric space, but in this talk I will just consider the domain to be a Banach space. Also note that if we take the class Lipschitz function and we take only the linear operators which belong to this class, we obtain a linear operator ideal in the sentence speech. Also, if we can add a norm to this class, such that for any Banach space E and F, this space I E to F is with this norm is a Banach space. The norm of the identity of R is 1, and also we have this inequality about saying something about the composition. Well, if we can define a norm that satisfies these three properties, we get a Banach Lipschitz operator ideal. And again, note that if we take all the linear mappings that belong to this class, we obtain a Banach linear operator ideal. Okay. Our first example is the Lipschitz examine operators of Farmer and Johnson that they was introduced in 2009. A Lipschitz mapping from E to F is Lipschitz examined if there exists a constant such that for every choice of x1, xn, y1, and yn, we have this inequality. Here, the x numeral belongs to the ball of the Lipschitz dual. And also, we can define the Lipschitz P-summing norm. All Lipschitz mappings from E to F, Lipschitz P-summing mapping from E to F will be denoted by pi p sub p supra L. The original definition of Lipschitz P-summing mappings was during when E and F are metric space. Note here that if we change the norm by the distance of a metric space, we have the same definition. We can extend it. This is, but well, as I said, we will consider just Banach spaces here. Farman and Johnson show that this class of Lipschitz function extends the P-summing linear operators. So, note that here the definition of Banach linear operator ideals is 7 years in the time of this definition. This work of Farman and Johnson is like as far as I know, is the first example of a Lipschitz function that extends, in this sense, linear mappings, linear ideals. From this example, this was very inspiring for many researchers, and from this time, inspired by this article, many authors have introduced a lot of Lipschitz mapping that extends some linear operator ideals. For example, we have extension of nuclear, p-nuclear, integral, p-integral, pitch integral operators, compact operators, and much more. So there is a natural way to construct Lipschitz Banach operator ideal from a linear operator ideal. And that I say that that is using the RNCL space that I will describe now briefly. For a Banach space E, we know by delta the evaluation map, and you can see that it can be as a function from E to the dual space of the Lipschitz dual space of E. And the Rn spaces and the RNL space of E is exactly the closed linear span of the image of delta. This space is also known as Lipschitz free Banach space, the transportation cost space, Bernstein 1 space, and I think there's many other names, but right now I don't remember. This is a very hard space to study. There are many researchers that by now they study this space. But well, I won't give some details of this space. I will just use some properties that we have of this space. First, we have a way to describe some elements of the RNL space. For a Banach space E, an element U belongs to the RNL space of E. We can describe an element here using a sequence of in little l1 and sequences xn and yn in E with this condition, and here we have the description. Also, using this description, we can compute the norm of that element. Why I put this description? Well, here we can see easily that this delta is in fact an isometry from E into the RNL space of E. And also we have a linear map from the Rn space of E to E, defined in this way. And this linear operator beta is just the left inverse of the identity of E. Is the left inverse of delta. Okay. So with all this, we also have the universal property of the RNS space for a Lipschitz function from E to F, we can get a unique linear operator from the RN space of E to the RN space of F, such that this diagram commute. And using this beta map I said before, we can get the linearization of a Lipschitz function. For any Lipschitz function f from E to F, we can get a linear operator LF from the Rn space of E to F, such that this diagram commute. Okay, how we can construct LF? Well, it's just this TF composition with that beta. So this LF is called as the linearization of this F. And also, if here we put, instead of F, we put a R, the real numbers, we obtain that the dual space of the Rn space of E is exactly the Lipschitz dual space of E. Okay, so we will use the linearization of a Lipschitz mapping to construct a Lipschitz-Banach operator ideal. Fix a Banach linear operator ideal, then A composed with Lip0 are all Lipschitz functions from E to F such that its linearization belongs to A. This is a Lipschitz operator ideal, and if we endow with this space with this norm, we obtain a Banach Lipschitz operator ideal. This type of Banach operator ideal are called of composition type. So what can we do with these spaces? What questions we have about this? So the first question is if A composed with Lip0 extender. So this way that we construct a new Lipschitz Banach operator ideal. We can use it to extend the properties that A can give us. The second question, and it's important, is does every Banach Lipschitz operator ideal, if every Banach Lipschitz operator ideal is of composition type. Why this question is important? Because if every Banach Lipschitz operator ideal is of composition type, we are saying that this new theory of Lipschitz Banach operator ideal is the same to study linear operators from the Rn space. So this new theory won't give us anything new to study this type of problem of the nonlinear geometry. We are just studying the Rn space. And also we have a third question, that is, how many Lipschitz ideals extend a fixed linear operator ideal? What means this question? Well, if we want to extend some linear property and describe it using Lipschitz properties, the Lipschitz mapping, sorry. Well, how many ways to describe it we have? We have just one, we have many. Well, we don't know. So these are our three questions that we have. So our first approach to this question, well, is we can give it using surjective Banach operator ideals. Which are surjective Banach linear operator ideas? Well, they are all ideas which are determined by the image of the operator. An example of surjective Banach operator ideas are all compact operator ideas, weakly compact, there are a lot more. So if I surjective Banach operator ideal that are composed with Lip0 extend a egg, yes. And how many Lipschitz ideas extend a fixed surjective operator idea? Well, more than one. And this, we show this with Professor Artur Lahia, and in fact, we answer this question using a specific surjective operator ideal, but using the same idea, one can extend this to any surjective Banach operator ideal. Okay, so we have a good first approach, but more in general, if we ask if A composed with 0 extend I, in fact, we are asking this. If we take this Lipschitz ideal, A composed with lib 0, and take all the linear operators which belongs here, that gives us exactly A, the same idea. Well, with Roman Villafañe, we show that if E and F are two Banach spaces and the domain is separable, then we always have this equality. Recall that the open question of the nonlinear geometry is if two Banach spaces, if two separable Banach spaces are Lipschitz isomorphic, if they must be linear isomorphic. So in the case of separable, we can always extend properties determined by linear operator to the Lipschitz mapping. However, also with Roman, we show that if we don't consider separable spaces, we construct a Banach operator ideal such that this inclusion is strictly and and don't extend A. So this way to construct Lipschitz operator ideal not always extends the linear operator ideal that we start. Okay, so for the other two questions, we need a bit more. We are saying here that what we did is that from a linear operator, we can get a Lipschitz linear operator using this composition type. And from a Lipschitz operator ideal, we can get a linear operator ideal just taking the linear operators which belong to this ideal I. So in fact, we can repeat these procedures, and from a linear operator, we can get another linear operator, and from a Lipschitz operator ideal, we can get another Lipschitz operator ideal. So which are the relation between this linear operator A and this new linear ideal, and also with this Lipschitz ideal I and this new Lipschitz ideal I? There's some sort of connection of relation of. So what we show that for a fixed Banach operator ideal A and a fixed Lipschitz Banach operator ideal I, we always have this inclusion, and we always have this inclusion. Also, since this way to construct from a linear operator to construct a Lipschitz operator ideal respect the inclusion, and also here, we get this equality. That means that this procedure if we start with a linear ideal, and we get a Lipschitz ideal, then we get a linear ideal, then a Lipschitz ideal, we continue doing that. Well, sometimes we stop. We can get, in some point, we don't get any new ideals. And this is equality we exploded. How we use this equality? Well, we get a criterion with Roman. If we have I, a Banach Lipschitz operator ideal, which is a composite of composition time, then we can say exactly which is the linear ideal which we have to put here to obtain this ideal I. It's exactly those linear operators which belong to this class. So as an application, we can see that the Lipschitz examine operators of Farmer and Johnson are not of composition type. Why is this? Well, first, if they were of composition type, since pi PL extends the p-summing linear operators, we will have this equality because of our criterion. Second, one can see that this delta map from R to the R's else space of R is one summing, and hence it's p summing for it's Lipschitz one summing and Lipschitz p summing from any p. So this belongs to the class of Johnson or Farmer, but if that delta belongs to this class, we are saying that the linearization of this delta must be linear p-summing. But what is the linearization of this delta is exactly the identity of the Rn cells space of R. And this map, the identity of this space cannot be summing because the Rn cell space of R is an infinite dimensional Banach space. Moreover, it's capital L1. So here we have a function which belongs to this class of the Farmer and Johnson p-summing and is not of composition type using pi p. So this ideal, this Lipschitz ideal of Farmer and Johnson cannot be of composition type. We can say a bit more. Recall that for a Banach linear operator ideal, we can consider its maximal hull that is determined by that is the biggest Banach operator idea which coincides with B, with A, sorry, in every finite dimensional space, and uses this relation that we have at the beginning and this equality that we had for separable Banach spaces and hence for finite dimensional spaces. We say that we can see that if we take a maximal Banach operator ideal, then this the Max composed with Lipschitz operator ideal extend A always. So as a consequence, we know by the Farmer-Johnson result that this ideal extends pi p of p-summing operators. Also, as p-summing operators are maximal, this ideal also extends p-summing operators, but they are not the same idea. So what we saw here, so does A composed with Lipschitz extend A? Well, sometimes, not always, but always in the interest cases. Which are the interest cases? When, well, they are when both spaces A and F are separable. The second is, does every Banach Lipschitz operator ideal is of composition type? And the answer is no. We have many, we show an example, but in fact we have many Banach Lipschitz operator ideal that are not of composition type. And finally, how many Lipschitz Banach ideals extend a fixed operator ideal? Well, more than one, and not only in the surjective case, not in the many case. Now you have to believe me that I show you just one example, but in many cases, just nuclear using nuclear operator ideals, integral operator ideals, and much more, we always have the answer of these three questions. Almost always we can extend a linear operator to the Lipschitz setting. A lot of time there is not just one way, and to do that. And finally, we can construct. Sometimes we can construct Lipschitz operator ideal which are not of composition type that extends a fixed Banach linear operator ideal. So that is our questions and some partial answer that we have. So let me finish with just a brief discussion. So why we study Banach Lipschitz operator ideal, and that was because we are trying to explain some linear properties or describe some linear properties using Lipschitz ideals. But this is the only way. So the question is, if we want to do that, we want to try to describe linear properties using Lipschitz ideals, Lipschitz functions. We must the only way that we have to do that is using the theory of Banach Lipschitz operator ideals. For this, to answer this question, first recall the Schauder theorem and Pitt theorem. First, we have that a linear operator is compact if only if its transpose is compact. This is Schauder theorem. And Pitt theorem states that all operators from little q to little p, when q is greater than p, are compact. So as a consequence, we can study the transpose of any linear operator from LQ to LP, and we have the transpose is compact. So can we say the same about a function, a Lipschitz function from LQ to LP using this Lipschitz transpose? This is a linear mapping, so the question is, if this linear mapping is compact, we can say something about F. In the linear case, yes, we can say something. If the transpose is compact, then this operator is compact. But what happened here in this case? So recall the universal property of the RNL space. If we have
okay, so I think I lost Pablo for a bit.
So the question that we have is that if this Lipschitz transpose has some property, some linear property, we can say something about this Lipschitz map. So recall, as I said, I don't know. Okay, recall that this universal property of the RNL space, any Lipschitz function from E to F, from any function f from E to F, we can obtain this linear operator TF from the Rn space of E to the Rn space of F, such as this diagram commute. So this Lipschitz transpose is exactly the linear transpose of this TF. So if we are asking, for instance, if this map is compact, we are saying that this map is compact. So using again the Schauder theorem, we are saying that this map is compact if and only if this TF is compact. But one of the conditions of a class of Lipschitz functions to be a Banach Lipschitz operator ideal is that the identity map belongs to I. If we apply this universal property to the identity of R to R, we obtain here the identity map of the Rn space R to the Rn space F. Sorry, this is the identity of the Rn space of R. So this map can never be compact because, as I said, this is capital L1. So if you want, you can ask what happened with this type of maps that this Lipschitz transpose have some linear property, but the answer, you can never give the answer of this question using the Banach Lipschitz operator ideal. These maps, these Lipschitz maps that have some property, the Lipschitz transpose, don't fix here in this theory of Banach Lipschitz operator ideals. Okay, so that's all I have to say. So thank you very much.
Okay, any questions for Pablo?
I have a question. Are there many cases? You said that in most of the cases, there are more than one Lipschitz operator ideals which extend a linear operator ideal. There are cases where there is only one, or in all the concrete examples, there is more than one.
We don't have an example of a case that there's just one extension. Right now, Nahuel is trying a way to construct many ways to extend a linear operator. So I think that
there is always more than one.
There's always more than one, and if not always the case, perhaps you have to search for a specific Banach ideal that have this one extension. But I think that no, I think that always you will have many extensions.
Does it make any sense to think which is the biggest one, the smallest one, or something like this, as we do with?
Okay, I think that the smallest one can give you some answer, because I don't say here, but you have maximal and minimal linear operator ideal, you have maximal and minimal Lipschitz operator ideal. So if you if you can find the smallest way, the smallest ideal that extends a minimal Banach linear operator ideal, and that is a minimal Lipschitz operator ideal, then probably you have exactly what that linear, that non-linear, that metric property that can extend the linear property that you want, but it's very specific.
Okay.
It has sense, yes, but I think that it's very difficult to answer that.
Okay. Okay, thank you. Nice talk.
Thank you.
Any further questions for Pablo? Okay, if not, we thank again our speaker.
Thank you very much.